Hello again. This little video is about extending a field. By an element. So first about the first word in the sentence in the title. Field extension is a generic concept which we'll use a lot in the future. If we have a field and if we have another field and if we have a relation between them, homomorphism, well, everything is unital, so let's look at it as a unital homomorphism. Then because this is a field, and being a field it means it is simple, no kernels, this homomorphism must be an embedding. So any relation between the fields, any unital homomorphism has to be an embedding. And such a situation is called a field extension. With E obviously extended in the field F. So let's look at a specific type of such extensions, namely let's just imagine that we have an element in the larger field and that the whole field can be, any element in this field can be constructed using arithmetic from elements in the smaller field F and this chosen alpha. So that is the first meaning of the notation. The field can be reached, any element in it can be reached by doing arithmetic and starting with elements of the smaller field F and this one single element alpha. And that case is called a field generated by a subfield and an element. So let's look at what are the options in such situation. And we will look at this situation through the ring theory. So what the ring theory will give us first is a homomorphism of rings. Let's start with polynomials in the variable t with coefficients in the smaller field f. And polynomials you can look at as instructions, algorithms of computing something by doing arithmetic operations and using elements of f. So doing these arithmetic operations and using as the input t using the chosen alpha, we have a way of evaluating any polynomial on alpha and turning it into some element of our extended field E. So really it works for any polynomial and it gives what we call the evaluation. Let's call this homomorphism, this is a ring homomorphism, let's call this homomorphism evaluation homomorphism on alpha. And as with any homomorphism from a ring somewhere else into some other rings, we have a possibility for it to be injective or not. So this dichotomy we used before defining the characteristic of a field. Now I want to use it in a slightly different fashion. And this dichotomy is controlled by the kernel being either 0 or not. So if the kernel is 0, if this homomorphism is an embedding, let me write it again, I have my polynomials and they're sitting inside the field E. But now let's remember that E is also a field, and so any polynomial has to have an inverse in. And that means that we have to go through the rational construction, a field of fractions, and that is also called the field of rational functions. So that has to sit inside E. And if E is just one of those fields extended fields extended by a single element, then this has to be an isomorphism. So we really described this field in this situation when the kernel of the version homomorphism is 0. We described it in abstract terms. It should be indistinguishable, it should be isomorphic to the field of rational functions. So namely it is a field of ratios of two polynomials, and the denominator is a non-zero polynomial. Let's look at the second possibility when the kernel is non-zero. Well, it's not really just one simple case, it's many cases depending on what the kernel is, but what we can be sure is that the kernel is generated by a single polynomial. This is a principal ideal ring. And this polynomial has to be irreducible, because otherwise we'll have zero divisors, and inside the field it's not possible to have zero divisors. So looking again at the homomorphism of evaluating on alpha, now we have a factorization into surjective map and epimorphism onto the quotient by this polynomial, followed by an embedding. And again, this is evaluation on alpha, so really what we are looking at here are all the values of polynomials on alpha. And we have an algebraic relation on alpha, so the fact that this is a kernel is just saying that p on alpha is 0, and any product of p polynomial with any other polynomial evaluated on alpha will be 0. So that is an algebraic relation on alpha. Alpha powers with some coefficients from f will have to be 0. That's the polynomial relation. So now we're saying that all values of polynomials on alpha are closed under addition, of course, subtraction, multiplication, and division, because this is a field. And so we have E described in here. That embedding is actually an isomorphism if E is generated by alpha. And so in this case, in the second case, E will have to be isomorphic as an abstract field to the quotient of the polynomial ring of f by this irreducible polynomial little p. So the first case is called transcendental extension, and the second is called an algebraic case. And that is a dichotomy inevitable for any extension by a single element. The first example, which I want to bring now up, is the field of 4 elements. We analyzed it in the previous video, and we saw that it has to be generated by a single element, we called alpha, and as an abstract field it becomes the quotient of the polynomials with binary coefficients by the following irreducible quadratic. And the real next sort of class of examples would be about complex numbers. So I'll really draw a line here. Then let me start with a complex number. We'll call it alpha. So what now I can do, yes, I have to mention before, but be aware that this notation, a field and then brackets and something in between them, some element or some variable, are confusing, because these and these are different things really, but effectively they are the same. So be aware of this overload of the particular notation here. So back to alpha. Alpha is a complex number. Let's now use this notation one more time and denote Q of alpha as the smallest field. Let's define it as the smallest field containing rational numbers and alpha. Well, you could see that that meaning fits into this scheme, that really this will be a field extension generated by rationals and a single element alpha. So if we define it to be the smallest field containing rationals and alphas, we could see that this indeed fits into the satisfies the condition here. It is an extension of rational numbers by single element alpha, just by the construction. So let's look at its possible structure. This dichotomy predicts what it should be, either a field of rational functions or a quotient of polynomials. So this dichotomy really says something about complex numbers. They are not all made equal. Some of them are algebraic. It's a second case. It's when their extension is a quotient by a polynomial. And that means, literally, if we unpack the statement, that there is a polynomial with rational coefficients, or rather polynomial with rational coefficients, for which alpha is a root. So algebraic numbers, and that is a historic definition of them, algebraic numbers are roots of polynomials with rational coefficients, or with integer coefficients for that matter. And we can always choose this polynomial to be irreducible. If it's not, we can look at its irreducible factors and choose the one for which alpha is a root. And otherwise, if there are no polynomials for which alpha is a root, if alpha is not a root of any polynomial, alpha is called transcendental. And you could see by some counting arguments that majority of numbers are transcendental. Majority of complex numbers are not roots of polynomials, but really the majority of interesting numbers are. Well, proving that something is algebraic is relatively easy. You just have to go through powers of alpha and see if there is any relation between them, any linear relation, and such relation will be a polynomial for which alpha will be a root. Seeing that something is not satisfying the scheme, is transcendental, is way harder, and it took great effort from mathematicians in the 19th century to prove that, say, pi or e are transcendental. So they're still very interesting numbers, but it's way harder to prove that something is transcendental rather than algebraic. So just to finish, algebraic number is such that we will have an isomorphism of its field, of the field constructed from it and rational numbers, with the quotient of polynomials by some irreducible polynomial. And you could see that this irreducible polynomial is effectively unique if it's made monic. And such polynomial is called a minimal polynomial for algebraic. And alpha transcendental, extending rational numbers will give a field which will be isomorphic to the field of rational functions. We will continue in examining algebraic and mostly algebraic numbers in future episodes. So stay tuned. Bye.